it's been pretty amazing to be kind of at the forefront, at the cutting edge, to see all the luminaries in the field, and you find out that these big names are just people with a lot of common interests that overlap with yours, and who will only be too happy to talk with you about them.
Hello everyone, my name is Nahuel Espinosa, and this is implementing particle filters with ranges. A little bit about me first. I'm an electronics engineer from Buenos Aires, Argentina. I've been working as a robotics software engineer at CppCon since 2020. Before that, I had some experience with embedded systems. CppCon is a company that provides software development services around the world, with companies with headquarters in Argentina and Europe. And I worked mainly in localization and simulation projects. And lastly, I'm maintainer of an open source project called Beluga, which is an implementation of localization algorithms for compatible with ROS and ROS2. Before we start, I wanted to give you a look and show you exactly what problem we're trying to solve. This is a simulation of an autonomous mobile robot that's trying to localize itself in a room. It collects sensor data from LiDARs and the wheels, and using a particle filters, tries to estimate its position in the environment. The red arrows here represent different hypotheses for where the robot could be, and by computing a weighted mean of those states, we can get a pretty good estimate for where the robot actually is. Just as a quick overview, there will be a brief introduction to particle filters. I'm not going to dive into the theory behind this. I will also mention the ranges library, but it will be good if you already are familiar with this. And by the way, this is a 30-minute talk, so we will spend most of our time in an implementation walkthrough for this particular problem. And so, for starters, Bayesian filters are algorithms used to estimate the internal state of a dynamical system using given noisy observations and random perturbation in the system itself. The state can be anything from position to velocity to orientation, or a combination of variables. And we have a probabilistic distribution called belief that we want to update as we incorporate information from the environment. So we do that in 2 steps. The first step is called prediction, where we incorporate transition data for our state. And then there is the update stage, when we use observations from the environment to change our probability distribution. As long as we incorporate more information from the environment, we get closer to estimating the true state of our system. Particle filters are a type of Bayesian filter where the posterior distribution is represented by a set of particles. Each particle is a single hypothesis of the state of the system and has an associated weight. This weight is proportional to the likelihood of that particle being the true state of our system. So the particle set as a whole acts as a discrete distribution that we can evolve over time. In these algorithms, the prediction step consists of computing new states for each particle based on the transition model, and the update stage consists of computing weights for each particle based on observations. And there is a step during the update stage that's called resampling, and what we'll do is duplicate particles with high weights and eliminate those with low weights. The reason for that is that we want to keep our distribution representative of the state we're trying to estimate. Monte-Carlo localization algorithms are particle filters applied to the robot localization problem. So the state we're trying to estimate is the position and orientation of the robot in the map, and the transition data comes from control commands or odometry, and observation data comes from sensors like LiDAR, cameras, or others. This is MCL in action. Now to ranges. Ranges is an extension and generalization of the algorithm and iterator libraries. Since the beginnings of C++, we have had algorithms that take iterators as input. Since C++20, we now have a formalized range concept, and we can pass ranges to our algorithms directly. And we also have views, which are lazy ranges that where the computation happens only when we iterate over them. An object that takes a range and generates a view is called a range adapter, and these adapters can be composed in range pipelines, producing nice and declarative expressions like this one. There's also, in C++23, we got the capability of implementing user-defined adapters that are compatible with the ones provided by the STL. And we also can materialize ranges into non-view types. So we could create, given a range or a view, we can create a container or initialize a container using the to adapter. Also, we could actually create anything that takes a pair of iterators. As you can probably begin to see, particle sets are ranges, and particle filters are algorithms applied to them. So the ranges library provides the tools to write these algorithms in a way that is easy to read, less error-prone, and easy to reuse. Hopefully, we will show that here. We will start with three main concepts for our implementation. The first one is a particle-like object, which is an object that has two members, a state that could potentially be anything, and a weight that must be convertible to double. We have two callable concepts. The first one is a state update function, which, given a particle object, can take its state and compute a new state and reassign it. So this is our transition model from before. And we also have a reweight function that can take a state of a particle and compute the likelihood of that particle being the true state of the system. We can also define a filter function that should perform two steps. First, it will take three arguments. The first one is a particle set. Here, we're taking stud vector for simplicity, but this can be generalized to all kinds of containers. And also our two update functions. The two steps it needs to perform are updating all the states and weights of our particles and resampling the particle set. So we can start with our implementation using utilities from the standard library. The first one we're going to use is StudViews transform, which we can use to generate views into our particle set for different properties of our particles. So in line 7, you can see that we're passing a pointer to data member to the transform adapter, and this will create a view over all the states of our particles. And in line 8, we can pass a pointer to data member to the weight and create a view over all the weights of our particles. There is no computation yet. This is just a declaration. And we can then do some work by using studRanges transform algorithm to basically, for each one of the states of our particles, we want to call the state update function and update that state and do basically the same with the weights. So after this point, we have our particle set has all the states and weights updated and ready to be resampled. So in the resampling step, remember that we need to keep particles with high weights and eliminate particles with lower weights. One way to do that is by using our particle set as a discrete distribution and sample from it using the weights as a probability. The standard library provides a class that does exactly that. That is discrete distribution. And here we're using it, but it cannot be constructed with a range. It doesn't have a constructor that takes a range. So we can use the studRanges2 adapter to materialize our weights into this discrete distribution class or instance. And lastly, we need to create a new particle set and use the values returned by our discrete distribution to sample or take particles from our original particle set and initialize the new vector. As you can see, there's a for loop here that's accomplishing several things at once. Since we are using the ranges library, what I would like to write is something like this. This is a range pipeline that with 3 steps. The first one is generating random samples from our original particle set. Here it says with replacement. That means that we can draw the same particle more than once. And this is an adapter that doesn't exist in the standard library, so we would have to implement it ourselves. The other two are already utilities that you can use now in the standard library. Take n of those samples and create a new particle set. The idea here is that we could replace any or even add steps to this pipeline to modify our resample algorithm in a way that's declarative, and you can really see the intention behind the code. So to implement our sample view, just as a note, there is a std-ranges sample algorithm in the standard library, but it is not quite what we need here because first, it is an algorithm, so it is applied eagerly. It needs a fixed size for the sample. It samples without replacement, so you cannot draw the same particle twice, and all the elements have the same probability. We need exactly the opposite, and I called this adapter sample to keep the slides code readable, but it should probably be called something else, like multinomial sample or something along those lines. The definition for our adapter will be given a particle range and a random number generator, RNG, generate a lazy computed infinite sequence of random samples with replacement. So this is what we want to generate. This is the expression that must create a view. And I will show 3 possible implementations for this using standard library utilities. Hopefully, we can learn something about ranges in each one of those. So the first implementation one could think of is using std-generator, which basically can convert a coroutine into a view. And as long as the coroutine yields values from it, you can, as long as you iterate over the std-generator view, you will get the values yielded by the coroutine. And I'm going to break down this code really quickly. There are 3 template parameters. The first is a range that must be random access because we will be literally jumping around randomly by taking samples. The second parameter is an RNG. And the third one is P, which is the value type of our range that must satisfy the particle-like concept we defined before. The function will return a std-generator instantiated with a const ref to our particle, and it will take our particle set by forwarding reference, and an external RNG by reference because we maybe want to share that generator with different random generators in our code. The first step would be instantiating our discrete distribution, similar to what we did before, this time in a single pipeline. There's not much to explain here. And then in an infinite loop, we will yield particles from our particle set using the values from our distribution as indices. So this kind of works if we see some examples. If we pass a null value reference to an existing range, this works just fine. But there are some lifetime issues if we pass a temporary, because in the second example, if I create an output view with a temporary, that will be destroyed before we get to iterate. So we need to fix that. One way to fix that would be taking the range by value, which works, but it is not ideal since now we're forced to copy the container when we call our function. So we don't want to do that. But passing by value is something that we should consider, and something that was meant to be passed by value is a view. So we will modify our function to take a view by value. See how I added in line 2 the requirement that the input range is a view. And this is OK, but of course, now our code doesn't compile because std-vector is not a view. We can take a look quickly at the compiler error, which is not that bad in this case. If you have worked with ranges, you know. But this is very readable. It says basically that std-vector is not a view, so we have to provide a mechanism to fix that. And it will be very easy. As it's continually said in this conference, adding a new layer of indirection will fix almost any problem. In this case, we can our original function, we can rename it as sample input, and we can create a new function that can take any type of range, any viewable range, and use std-view-sol to convert it into a view. What this does is, depending on the type or the value, the type and value category of the thing we pass to it, it will create the appropriate view. If we pass a view, we will get a view as return value. If we pass an L value reference to a range, we'll get a ref view. And if we pass an R value reference to a range, we get an owning view. So this will do the right thing. If we see the result, the second example doesn't compile yet. And here is the compiler error. I couldn't fit it into the screen. But buried down there, I promise there is some useful information. I formatted here at the output that says that there's so much for operator pipe. And the reason is that if we try to pipe our owning view without moving for it basically that won't compile. We need to move our owning view into a pipeline for it to work. But we don't want to do that here because we want to keep the view to generate samples from it. So this is a special case in which we need something else. And the workaround is using ref view. So that will allow us to iterate over our owning view without having to move from it. And it is still owned by the coroutine. So this is the last piece we were missing. All this code works. Our two expressions compile. We would be done by now if it weren't for the case that there are some performance issues with this implementation. Currently, compiler support is not there yet in terms of optimizing all the coroutine stuff. I wrote a quick benchmark to test this implementation with a baseline case where I use a simple for loop. And there is some overhead when using stud generator as a view for this particular case. I'm sure that stud generators has a lot of applications. And in this case where we need the calling to an RNG is not that expensive, we can see some overhead for using it. But we can explore other options. The first one would be using something that hasn't been standardized yet, that is studvis generate. This is a view that exists in the original range v3 implementation and basically takes a functor and generate values by calling repeatedly that functor. So this would basically solve the problem without having to rely on coroutines. This is a tier 1 candidate for CppCon so hopefully we will get it then. For now, we have to rely on other options, but yeah. The third option is implementing our own custom view from scratch, which hopefully I can show that it's not that hard for this case, especially because our sample view is basically an input range, so those are the easier ones to implement. The design choices we're making here are that our sample view will have 4 members, a base view from which to generate samples, a discrete distribution instance, a reference to a random number generator, and a cached first iterator to the base view. The iterator class will simply wrap the base view iterator with a pointer to the sample view. And the idea is that every time we increment our iterator, we can ask the parent view for a new iterator to the base view and jump to a new position. And to implement this, we need to define a new class, sample view, that will inherit from view interface. This is a CRTP class provided by the standard library. And basically, we'll implement the right interface for our view depending on our implementation of begin and end methods. The requirements here are the same as we had in the function before. So the constructor will take a base view by value, the generator by reference. We will remove the copy constructor and copy assignment operators. The reason is that we are storing a discrete distribution class initialized, and that is not cheap to copy. So when we implement these things, we want to make sure that they are cheap to copy or not copyable at all. So this is the solution. And begin and end methods are very straightforward. Begin will return a custom iterator type that will do all the work, and end will return unreachable sentinel since this is an infinite range. There's a helper method here that we can define in the parent view to create a new iterator to the base view based on the value returned by the discrete distribution. And the iterator class is an input iterator. It only needs to implement the input iterator interface, and it needs to wrap the base view iterator. And every time we call the increment operation, we will call the next function and store the new iterator internally. So this should cover all the iteration logic. There are a couple more pieces we need for this to work completely. One of them is a deduction guide to actually construct our sample view from any range, not just views. Instead of defining a separate function as we did before, in this case, the deduction guide can use the meta function alt, which is the equivalent to the studViews all function we used before. And this will make it so our view can be constructed from any range. The sample function here will simply forward the arguments to the constructor of the sample view, but we will come back to this later. So this is our implementation. Comparing the performance with the same baseline as before, the custom view implementation almost has no overhead compared with the baseline. And even in some architectures or CPUs, I saw that the custom view is better. And this probably is a statement for how bad my baseline was. But by the way, the code for the performance and for the benchmarks will be available on GitHub. So it is inside a container, so all the dependencies are there, and you can try to reproduce this. So now we have an expression that can return a view, given a particle set and a generator. But to make this a complete adapter, we will need these two expressions to also be valid. So what do we need to fix? We need to create a new overload for a sample function that takes a single parameter, the generator, and can create a closure object. This object can later be used to create the view. And so our range adapter closure object is a range where these two expressions are valid and equivalent. But basically passing the range or using the pipe operator with another adapter. So to implement that, this is the code we had from before, we can add a new overload that takes a single parameter, and we need to return something that we can then use to create our view. And that something is an instance of a sample closure type that we will define here. This will inherit from yet another CRTP class from the standard library. This is range adapter closure. And what this does is makes our type pipeable with standard adapters. So this is what was added in C++23 to support user-defined adapters. And you can notice that the call operator here takes a single range. The rest of the arguments required to construct our view must be passed at construction time in the constructor. So this is no big deal. And now we have a class that can be instantiated with a generator, and we can later call and pass a range to create the view we need. Now, our overload will simply return an instance of that sample closure object. So to recap, now all these expressions work. Typically we need 3 elements to create a custom range adapter, which is basically a view that class that implements the main iteration logic. We also need a pipeable object that captures configuration per arguments and can create a view given a range. And we also need a function that can create a view or a range depending on the arguments. I'm not going to talk about nibloids here, but typically in the standard library, instead of defining sample function, you would define a nibloid or customization point object if you're writing a library that makes sense. To put this to the test, let's try to see if this abstraction is extensible enough to support different cases. So instead of having all our particles stored in a single continuous vector, let's say we have 2 containers, one for all the states and one for all the weights. This would be analogous to having a structure of array layout in memory. And we can still use our adapter with a few small tweaks. We can define a particle ref class that holds references to external state and weights. We can make sure with the static assert that that class satisfies the particle light concept. And we can define 2 separate functions, one that can create a particle ref class. Basically, this emulates a constructor from 2 references. And one that, given a particle by reference, can return a reference to its state. With all these helper functions, we can write this pipeline. And this works. To me, this is amazing. You can zip transform the 2 containers to generate a new particle container that is also random access, because the 2 containers are random access. So all the requirements for a sample adapter are satisfied, and we can use it to generate 1,000 samples, transform that back to a state, and convert that to a state vector at the end. So, and from my testing, this has no overhead compared with a baseline implementation using for loops. But I hope you can see this is much more readable, maintainable, and extensible. If you want to add anything in the middle, you can. Just as a note, before I leave this slide, our adapter is not entirely lazy, like the ones provided by the standard library, because constructing our sample view will actually iterate over all the weights of our particles to instantiate our discrete distribution. But the expensive part actually here is calling the RNG. So I think we should be fine. And so here are other examples for cases where we would want this adapter in localization algorithms or resampling algorithms. Here I'm showing classical MCL, where we take a fixed number of particles and initialize the new container with that. We could also replace that take adapter with take until KLD, which basically says that we draw particles until we have enough to represent the posterior distribution, and basically uses information from the state of each sample to make that decision. So this is already very extensible. And the last example I wanted to show is a recovery strategy for a localization algorithm. This is a known solution to the kidnapped robot problem. You have your robot localized in a certain place in the environment, and you move it. You want the localization algorithm to be able to recover. And one way to do that is by injecting random particles from the map. So if you happen to inject a particle that is more likely than the ones you have in your distribution, the particle filter will converge to that new location and recover your estimate. So these are some examples. Of course, this can be extended, and the idea is, yeah, you can do whatever with this. Before we leave, some practical recommendations regarding working with ranges. So leverage concepts and static assertions as much as possible. This is basically telling the compiler to catch errors for you sooner rather than later. Beware of semantic requirements. Those are requirements that cannot be checked by the compiler, so you have to pay extra attention when you're trying to implement a sample adapter, a view. It is useful to keep that in mind. And if you want to learn more about ranges, of course, watch the talks. There are a lot of great talks related to this topic, but also check out the papers and source code of adapters implemented in the standard library. Once you start grasping the basics, they are really useful to understand and give you ideas on how to implement your custom adapters. And if you're curious about how to get this implemented in CppCon 17, I wrote a quick example using range v3, which was the basis for the proposal for the standardized version of ranges. And yeah, you can check it out. There are some differences because the ranges proposal evolved, especially in CppCon 23. But things are not that bad. The only thing I would say I miss here is the concepts as implemented in CppCon 20. So yeah. If you want to see a more complete example of some of these ideas, we have a project called Beluga, which is an open source implementation of MCL algorithms. And it is compatible with widely used robotics frameworks like ROS and ROS2. And some final remarks. We can use the STL to implement composable range adapters for domain-specific applications like particle filters. And ranges are useful to implement complex algorithms in a way that's straightforward to write, easy to read, and easy to reuse. Thank you all for listening. The code for the slides, the benchmarks, and examples will all be available on GitHub. And yeah, let me know if you have questions. Thanks.
Hey, it was a really excellent talk. Thanks a lot for that. I just had like a weird question about one of the slides where you had the two separate containers with states in them.
Yeah.
I was kind of wondering what was the thing going on? Yeah, right there with like the states having like a vector of 50 doubles.
Yeah. So yeah, I forgot to mention that. I intentionally added a state that's expensive to copy. So I wanted to make sure that I would avoid unnecessary copies in this implementation, and this actually does that.
Thank you.
Thanks. Great. Seems like there are no more questions. Thank you all for coming and hope you have a great conference.